Okay, today we are going to kind of zip through Fourier transforms and how we can use them. And as you can see, just as an overview of why we care about these things, apart from the things that we talked about last time, like signal processing, the real general utility of Fourier transforms is making a problem easier. And what we're going to see today is that there are two ways that it can make a problem easier, and you'll see this in your homework. One is that a Fourier transform, because of the properties of the derivatives of a Fourier transform, can make a partial differential equation into an ordinary differential equation, and often one that we can solve pretty easily. And we'll do that in an in-class problem. The other reason why we can do this leads us right into the last class, which is that if you have an ordinary differential equation and you Fourier transform all of it, you can create an algebraic expression, solve that expression, and then use the inverse transform to find the solution. And often that's easier than doing the actual problem. So that's where we're headed today. Basically finishing up Fourier transforms. With respect to some announcements and some reminders, just a reminder that your last homework is due on Friday, end of the day, whenever. As long as you turn that in and make an attempt at every problem, then I'll let you take the final if you like. I still have to compute the grades. This last week has been busy with meetings, as you might imagine. But I should have that updated today, and you'll know where you stand, essentially. And no judgment, it's totally okay. If you don't want to take a final, I can't blame you. I don't know that I would want to either. But I'd like you to cover this last bit of material. So that's why we're finishing off this week. So make sure you do that. To help you with that, I have my normal office hours today, but I know that a number of you are in advanced lab, and I did receive some email about office hours today. Because of some of these extra meetings, I can't expand my office hours today, I'm afraid. I'm really sorry about that, but I will have some additional office hours tomorrow, 2 to 3, and if I can, I'll squeeze in some more. If you can't make those, let me know. The other announcement or reminder is that we're having the senior tea tomorrow at 4 o'clock, so please zoom in to that. You should have received the link from Willa. We'll be doing our annual awards. I'll be sending out an email to our graduating seniors in 3-2 majors so that you can do the usual thinking back and thinking forward business that we do at senior tea. You'll have to provide your own drinks. Finally, for the first time, I don't have to drink sparkling cider. I can have the real thing at one of these things. Awesome. There's always a good side to this. All right. Any questions? All right, let's get started then. First part of this is to look at some properties of Fourier transforms. And in particular, we're going to start with the transform of derivatives, because that's where the game is, really. And just note again, if you're using a different version of the text, or if you're using supplementary text, the notation convention is all over the place. So I will try and be consistent. The thing that you should realize, your book does mention this, is that we often use as the transform variable omega, and that's because of the signal processing nature of application, but it doesn't have to be that. So we'll stick with that and maybe use alpha in a couple of examples just to make it clear that we're not just talking about going from frequency space to time space. So in that vein, let's consider, say, g of omega, which would be our transform. So 1 over root 2 pi times the integral from minus infinity to infinity of f of x e to the I omega x dx. And then what we want to consider is what is, say, g1 of omega. In other words, how do we evaluate the derivative of f? So df dx, and we're taking the derivative with respect to x times e to the iw, or omega x dx. In other words, we know what the Fourier transform is. What is the Fourier transform of the derivative of a function? What we can do is integrate by parts. So, right, by parts. We get g1 of omega. It's an ugly omega. g1 of omega is equal to e to the I omega x over root 2 pi times f of x would be our evaluated part, evaluated from minus infinity to infinity, minus I omega over root 2 pi times minus infinity to infinity f of x e to the I omega x dx. The trick is, and this is usually the case for the things that we're interested in, if f of x goes to 0 as x goes to plus or minus infinity, we get our canonical result, which is that the first derivative, the Fourier transform of the first derivative is just minus I omega times the transform of the function. And we could keep going for second and third derivatives. So we can write this as the nth derivative, or the transform of the nth derivative is just equal to minus I omega to the n times that original transform. So you might see this is actually a stunningly beautiful result. Actually, it's one of the nicest results that we've done all term, because you can, if you think ahead to the kinds of differential equations that you encounter in physics and as well as math, you can imagine extremely complicated ordinary differential equations where you have multiple derivatives, multiple order derivatives equal to functions. And if you take the Fourier transform of everything, that is, you multiply everything by e to the I omega t, say, or x, and integrate from minus infinity to infinity, you end up with basically an algebraic expression in which you can solve for g of omega. Once you know what g of omega is, you do the inverse transform, and you solve the problem in transform space. So let's look at an example. Well, before we get to an example of that, a couple of identities, and these are things that your book covers, but these are particularly useful. I'm going to write it sort of the way that your book writes it, which is to say the Fourier transform of the gradient, right? So that it becomes a function of k. We're using the three-dimensional Fourier transforms. We're taking f of r and we're transforming it into k space, but that could be omega t, doesn't matter. This is essentially what we just did, minus I k times g of k. These are all vectors. So if you're looking at the gradient of something, that's always going to be the case when you do the Fourier transform. The Fourier transform of the Laplacian is, as you might expect, just minus k squared times the Fourier transform. And there are others. You should also note to something that's often useful, say the Fourier transform of the delta function. That is the integral of 1 over root 2 pi times the integral from minus infinity to infinity of delta of, let's use t, e to the I omega t, right, is equal to 1 over square root of root 2 pi. In other words, if you think about some of our definitions of the delta function, d.6 gets us back to one way of defining the delta function. There's a normalization constant in there, but essentially this is one way of expressing the delta function. This will be useful, especially in the homework, but as we do other problems, especially since part of the process here is take a problem, multiply it by this exponential factor, integrate over the region from minus infinity to infinity, and then look at what your transforms give you. So those equations, d.2 through d.6, are the things that you will probably use more than anything else when you do Fourier transforms. Okay? I can't stress enough how beautiful this is. This is just awesome. It really is. Okay, so let's look at some examples. We'll do one example, then you'll do an example. So one example is, let's look at the wave equation. This is a good example of how we turn a partial differential equation into an ordinary differential equation. So we might have something like d squared y dx squared is equal to 1 over v squared. Let's see, I'm going to do this. D squared y dt squared. Right? So there are a number of ways you can do this. You can Fourier transform in x. That is, take the Fourier transform of everything. This would be take the integral from minus infinity to infinity of d squared y dx squared e to the I, and we'll use alpha as our transform variable, alpha x dx. That's equal to 1 over v squared, assuming that's a constant, times the integral from minus infinity to infinity of d squared y dt squared e to the I alpha x dx. All right, immediately I hope you can see why it's important that we recognize the result of d.6, right? Because this can pop out of the integral, and then this is just our delta function, right? So that means that we have minus I alpha squared, and we'll call that capital Y as our transform. Alpha of t is equal to 1 over v squared d squared y dt squared. Okay. Where capital Y of alpha t is now 1 over root 2 pi times the integral from minus infinity to infinity of y of x t e to the I alpha x dx. Okay. In order to solve this problem, we need initial values, right? So in this case, we might have an initial wave function. So let's say, what do I have here? Y of x 0 is equal to f of x, right? That means that capital Y of alpha 0 is equal to 1 over root 2 pi times the integral from minus infinity to infinity of y of x e to the I alpha x dx, which is equal to, we'll call f of alpha, our Fourier transform. That means that y of alpha t is equal to f of alpha, but you notice now that we've separated variables we have essentially our usual expression for something like the wave equation, so that our temporal piece will be e to the plus or minus IV alpha t. And from that, we can write that y of xt is equal to 1 over root 2 pi. That is, we'll do the inverse transform. And the inverse transform is just the same, except with the reverse sign of the exponential. So we take our transform equation, that y of alpha t times e to the minus I alpha x, right, and integrate it over alpha, because we want this to be a function of x. And this becomes 1 over root 2 pi times the integral of minus infinity to infinity of f of alpha e to the minus I alpha x minus or plus d over t. In other words, we can't do anything more until we know what f of x is, but what we have shown is that y is now a function of x plus or minus vt. In other words, an outgoing wave and an incoming wave and an outgoing wave. Right? If we know what f of x is, then we've solved the problem. This is a little bit of a sledgehammer instead of a fine hammer to figure out a problem like this, but I think it's illustrative of what we can do with Fourier transforms. Right? We are transforming the differential equation to something that we can more easily manipulate. Are there any questions on that? All right. Then we're going to jump in with something that you guys can do. And I want you to do something similar. In this case, we're going to look at a diffusion problem. All right, so in this case, and this is just the general diffusion problem, you're going to look at the equation del squared n dx squared is equal to 1 over d dn dt, where d is a diffusion constant. What you need to do then is use the transform, the Fourier transform. So transform both sides. This should produce essentially an ordinary differential equation of, we'll call it n tilde, which is the Fourier transform. And I want you to find, let's see, we'll use the solution k. That is, we're transforming from x space to k space. Same thing as going from omega to t. So what you're going to need to do is ask yourself how you make this a Fourier, each side of Fourier transform. Evaluate the Fourier transform. Find what that expression for the Fourier transform is, that n tilde, and then find an expression for that in terms of k and t. Okay. Does that make sense? So the idea here is ultimately what you're going to be able to do is take this partial differential equation, which is not the most difficult partial differential equation to solve, I realize, but transform it into an ordinary differential equation and then write the solution. Now, I'm not asking you to transform it back using the inverse transform. What I want you to do is set up and solve for what the transformed n is. Give me a thumbs up if you understand what you need to do. Okay? All right. Let's see. All right, off you go. work out okay?
Yeah.
Get an
You just wanted
exponential?
us to get like the differential equation in
What's
terms
that?
of n tilde.
Yeah, just I wanted, yeah, you didn't need to do the inverse transform.
Okay.
Yeah, it's a little bit more, I'll go over that. It's a little bit more
Understood.
complicated because you need to complete the square in order to solve that. But what you should have gotten was an exponential, because once you've done that transform, all of a sudden you can, it's an ordinary differential equation. Work out okay?
I think.
Yeah. Get an exponential?
Yeah.
Okay.
Um,
I didn't ask to solve, you didn't have to do the inverse transform, just the transform. Right?
I really feel like all of these problems are like the same thing.
How so?
Like, I don't know, they don't seem very different to me. Like when you get an answer, like they're not very unique in a way. Like I feel like we're just kind of changing out letters and stuff. I mean,
Well, to a certain extent we are, right? But I mean, there are, if you think about certainly partial differential equations that are important to physics, there are only like four or so that are things that you see all the time. So the solutions to these are going to take on familiar characteristics. The trick is, especially when you do say the inverse transform and you have a particular initial condition, right? So understanding that you keep seeing this pattern is a good thing. It's what happens, how do you solve things once you have that. So anyway, what you should have seen then is if you basically, to do the transform, you multiply both sides by e to the ikf. And integrate from minus infinity to infinity. And you're integrating over dx. Okay? So this is dn dt dx. All right, so that's your first step. This becomes minus k squared, we'll call it n tilde. Again, that's the Fourier transform. And then this becomes 1 over d dt. Everything else becomes the delta function, right, or the transform of the delta function, right, which takes care of, essentially there's a constant in there of 1 over root 2. So if you do the transform, we're just kind of canceling out the root 2's. What this means then is the Fourier transform, say, okay, t here is now n naught tilde, right? Times e to the minus d, let's see, what am I doing here? K squared t, right? So to finish this problem, you need to transform back to real space. And this is actually there's a problem that's similar to this in the book for heat flow. So if we let psi be our transform function, n prime or n tilde, let's let a squared be d, and let k be omega, just so that the notation is consistent. You would find essentially the same thing. The Fourier transform for a heat diffusion problem would be psi of omega t is equal to some constant e to the minus a squared omega squared t. Oops. That constant we've identified as this initial value. If we want to dive into this a little deeper, right, we can specify what that value is, namely c is equal to psi of x0, some initial distribution of temperature or particles before diffusion. And what we're after is our lowercase psi of xt, or our lowercase n, that is the actual solution to this problem. In order to do that, we need to do the inverse Fourier transform. So that's 1 over the square root of 2 pi times the integral from minus infinity to infinity of this, call it psi 0, e to the minus I omega x, e to the minus a squared omega squared t d omega. And c omega is our essentially, or psi omega or not, is our initial function. We need to complete the square like we did last time. And so we have a squared omega squared t plus I omega x. We're going to have here is at squared omega squared plus ix omega minus x squared over 4a squared t plus x squared over 4a squared t. That's just the completing the square part. So this should all equal a t 1/2 omega plus ix over 2a to divide t to the 1/2 squared plus x squared 4a squared t. And if we put all of that in, that allows us to solve, that allows us to solve for psi of x. Because now we can pull out the constant terms. In the interests of time, I'm not going to go through all of that algebra. What you can find for this particular case is that psi of xt is equal to that initial spread times, or divided by a over 2t times the exponential of e to the minus x squared over 4a squared t. So there's a lot of magic that happens there, but that's just manipulating an interval. The big lesson here is that by using the Fourier transform, you're able to create an ordinary differential equation and solve it that way. In your homework, you have problem 20.3.6. This is a little bit different. Rather than transforming a partial differential equation into an ordinary differential equation, you're going to transform every piece of it. So every term of basically an ordinary differential equation. And from that, you can get an expression for G, which would be the Fourier transform. And in that case, you'll find whatever that expression is. Imagine basically if you had a differential equation that was x double prime plus x prime plus x squared or something like that, and then you do the Fourier transform of all of those pieces. Actually, let's not do that right now. And this equals some function f of x. We've seen how there are some ways that we have seen that you can use to solve this, but we now know that if we take a Fourier transform of all of these pieces, we can create an algebraic expression for the transform. Once we know the expression of the transform, to get f of x back, you use the inverse transform. So as advertised, one of the main things that I wanted to get to in this class was a way of solving differential equations that takes the calculus out of it and makes it an algebra expression. Now, in the case of Fourier transforms, you still have to do the Fourier inverse transform to get back the answer. In the terms of the Laplace transforms, as we'll see on Friday, there's actually a list of tables of functions, and it makes it easier to transform that into an algebraic expression and then transform it back into real space. But the whole name of the game here is take a problem that is difficult or impossible to solve in real space, transform it into omega space, k space, whatever it is, and then solve it there because it's easier there, then transform it back. Okay? Are there any questions on that? Okay. Hearing none, we'll move on. The last part of this section is a short section, actually not particularly short, but an important section on convolution theory. So what do we mean by convolutions? Have you ever encountered convolution before? No?
Is it like when you have, like, looking at the integral of when you have two shapes like passing by each other and how they cover different parts? And that's like a really bad description.
Well, no, I mean, actually, that's a really good qualitative way of expressing this. I mean, convolution itself comes from, I mean, the actual idea comes from folding two functions on top of each other and looking at that overlay. And the main idea here is that we're going to take two functions that have different arguments. And because of this process of folding them over and doing a Fourier transform, is that we'll have transformed these two functions with different arguments into functions that have the same arguments. And in that way, we're able to solve particularly questions that are related to quantum theory where you have to deal with complex conjugation. So you probably, even if it wasn't called that, saw convolution in quantum. You do see it in signal processing too, so you might have seen it in optics as well. Okay, so let's start with the definition. That was really good. the idea, I mean, and there is a picture in your book of considering, and it's kind of a classic example of, say, one function e to the minus y and convolving it with another function e to the minus x minus y. Basically a mirror about x halves. And we're going to fold one function on top of the other, right, in order to basically transform these functions into functions of the same variable. So the way we write this is f star g, sometimes in parentheses, and that is 1 over the square root of 2 pi times the integral from minus infinity to infinity of, say, g of y f of x minus y dy. Right? So that's just a straightforward definition where we have f of x and g of x and f of t and g of t. These are the functions. These are the Fourier transforms of those functions. In other words, we're going to try and move this in, basically use Fourier transform theory to see what we can say about these two related functions. Okay, so the immediate question is, what's the result of this integral, this integral that we've defined? Minus infinity to infinity of, say, g of y, f of x minus y, dy. And what we can do is relate it to Fourier transforms. Namely, this root 2 minus infinity to infinity, we have g of y, but then we can look at that other function and realize that we can write this as the integral from minus infinity to infinity of the Fourier transform, the inverse Fourier transform, right, f of t times e to the minus I t x minus y dt, and then all of that dy. So it's worth taking a moment to think what we've done here. We've taken this, right, that's equivalent to the inverse transform of the transform, right? If we did the Fourier transform of f of xy, we would get capital F of t. If we do the inverse Fourier transform of f of t, we should get f of x minus y, right? That's why there's an x minus y up here. That's why we've got this integral, right? And then we still have this g of y. So all we've done is define our function f in terms of its inverse transform. It's kind of this weird, we're going to transform it, but then inverse transform it so that everything's the same. Everybody cool with that? It's kind of like taking the square root and then squaring it, right? So this is equal to 1 over square root of 2 pi times the integral from minus infinity to infinity of f of t. We rearrange this now of the integral from minus infinity to infinity g of y e to the I t y dy e to the minus I t x dt. Right? But that's just the Fourier transform of g. Right? So now we have 1 over root 2 pi times the integral from minus infinity to infinity of f of t, g of t, times e to the minus I t x dt. So if we let x equal 0, so for the case at x equals 0, we have the integral from minus infinity to infinity of the Fourier transform of f, the Fourier transform of g, is equal to minus infinity to infinity of f, you know, if you be careful of these signs, minus y, g, y, dy. And that basically leads us to the Parseval relation, namely the integral from minus infinity to infinity of f of t, g of t, in this case, the complex conjugate of g of t is equal to minus infinity root, the integral from minus infinity to infinity of the Fourier transform of f of omega, g star of omega, d omega. So again, this is one of these really beautiful, simple results. But the real utility of this comes when we start moving, using this in, say, momentum space and momentum space representation. But the main idea here is that we've taken two related functions and we've related their Fourier transforms, their functional form, to their Fourier transforms, the integral of their Fourier transforms. The payoff then is when we consider momentum space problems. And you have seen this, or I'm assuming, I think you have. In quantum, you know that you can write, say, Schrodinger's equation in terms of spatial derivatives or in terms of momentum space, right? So this gets us back to that. In terms of spatial relationships, we know that psi star of x, psi of x, dx is what? What does that define? In quantum mechanics?
The expectation value? Sorry, Nick.
Well, it's not quite the expectation value, right? Because in order to do the expectation value, we actually have to do the integral.
The probability.
Say it again?
The probability.
Right, so this is the probability density, technically, that a particle lies between x and x plus dx, right? So this is the density between x and x plus dx, right? We also know that the integral from minus infinity to infinity of psi star of x, psi of x, this starts to look an awful lot like the Parseval relation, right? We know that this is equal to 1, or we hope that it's equal to 1, right? If it's properly normalized. And then, so we have the expectation value x is equal to the integral from minus infinity to infinity of psi star of x times x psi of x dx, right? So that's typically your starting point when you start dealing with, say, with the wave equation in quantum. You can do the same thing with momentum space. So here you have the same things, g star of p, g of p, dp is now the probability distribution for momentum between p and p plus dp. We know that this should be normalized, that is the momentum should be something, right? G star of p, g of p, dp is equal to 1. And we know that we can define an expectation value for p as g star of p, p, g of p, dp. All right. So if it's new, at least it looks familiar, and if it's not new, then I mean you've seen this before. The trick here now is to consider the transforms that we've been talking about today. So g of p, then, we can write as 1 over the square root of 2 pi h bar times the integral from minus infinity to infinity of psi of x e to the minus I pi x over h bar dx. Make sure I get this right. 5. And of course, g star of p is equal to 1 over the square root of 2 pi h bar minus infinity to infinity of psi star of x e to the I px over h bar dx. And if we wanted to be more explicit, we could write this in terms of three-dimensional space. So g of p equal to 1 over 2 pi h bar to the 3 halves, again, times some integral from minus infinity to infinity, psi of r e to the minus r dot p over h bar d cubed r. Okay. What's really cool here is that we've now written a function of momentum in terms of the Fourier transform of something in space. So you've done this before. Even if you didn't call it a Fourier transform, you know that you've dealt with problems in one realm and then looked at them at the other. For normalization, we use the Parseval relation. That is the integral from minus infinity to infinity of psi star psi dx is equal to, sorry, that's not a minus, is equal to the integral from minus infinity to infinity of g of p star g of p dp is equal to 1. In other words, we've got g of x, f of x, g star of x, g star and f. Right, so we have what we're, and I'm running out of time, so I will finish up with this next time. But the point of this section and in your book and in these notes is that we can understand basically 1/2 of quantum theory in terms of the wave function as a Fourier transform from space to momentum. Right? It's deeply part of what we do in quantum in terms of understanding the wave equation, is that these two are related by Fourier transforms from space to momentum and inverse Fourier transform from momentum to space. Where you solve that problem depends on what you're asking for and what makes the problem easier to solve. We'll do one example on Friday, and then we'll launch right into our last subject, which is Laplace transforms. Are there any burning questions since we're already out of time? You guys have been doing great. I know this is the last week and it's the penultimate class and you're hanging in there. But look over these notes again. This is taking what we've done over the last 8 weeks and really looking at the heart of what it is we do as physicists with especially problems in quantum mechanics. And it all comes down to this really interesting trick that we can go back and forth through. All right. Well, again, I have office hours today, and I'll have office hours tomorrow and on Friday. I'll see you. If I don't see you then, I'll see you tomorrow at the senior tea. And I hope you all have a good day. Bye.
Thanks, Meg.
Well,
Bye. Bye, Allie.
Hi, Rick.
Bye, Adrian.
Hello?